we will be talking really hardcore stuff. So I'm glad it's not morning slot. We will start with some system management bugs and actually firmware. But before I will be jump on the presentation, I want to shout out my research team, and they did a lot of great work to make all this stuff happen. And of course, to the vendors which has been participated on all these disclosures. So what we will be talking about? First, last year I've been talking about supply chain bugs and reference code and etc. So basically, things not get better. It's actually get worse. And today we will be talking about confidential computing and how really the silicon which we have today out of the shelf is ready for it. We will be talking about the problems which is breaking by design SLR for ring 0 and KSLR for ring, for ring 3 and KSLR for ring 0. This will be very interesting when we prove, we'll be show the demo, and it will be all public. You can reproduce on your machines if you want. Actually, all this stuff is broken by design. And of course, we will come back to the firmware and talk more about it. Let's talk about the supply chain. And Binarly actually disclosed over the year 400 vulnerabilities, and these numbers are just growing. And 200 it's still under the disclosure. The timelines for these bugs, it's actually ridiculous. Average it's 6 months, but in many cases it's get delayed, extended, and it's go beyond the 1 year. So some of the things, like private keys, not in HSM, it's actually happened, and MSI leak, it's proved. What is actually worst, sometimes private keys can be found on the GitHub. And unfortunately, this is GitHub account, one of the developers from Asus Tech. He's been working on Aeon platforms, which is used in ICS, and it's actually used by US companies as well. And all the firmware code, which is actually proprietary and belong to American megatrends being public, include the private keys. But private keys, which has been on this repository, it's not being belong to American megatrends, it's been belong to Intel and unlock the debugging capabilities as an orange unlock and allow people to actually debug any platform which can unlock with this key. This has been very interesting, and it's one of the supply chain problems we discover. Another one, it's actually a small bug which we found as a bonus vulnerability for our last year Black Hat talk. Problem with this bug, nobody pay attention to it. We actually made a pull request to EDK2 like almost 2 months ago, and nobody fixing it. But this vulnerability, it's very easy to exploit. We shared the POC. Unfortunately, it's not escalates as code execution fixing faster. This is denial of service. But it exists on many, many, many machines, include some critical infrastructure and energy sector. 100 plus days under the disclosure. So who cares about supply chain, right? So another thing is reference code vulnerabilities. And this one's been found in Qualcomm and Lenovo ARM-based devices. And I want to shout out to the Qualcomm. It's probably been the fastest disclosure we ever made. They kind of like make it to the 90 days timeline. Only one company which has made it. For entire history of our disclosure as a Binarly team. But 8+ months later, we realized not all the devices still fixed. And I don't know if Dave Waston here in the audience. So I have a good news for you. You have more job done. And basically, we've been looking on these vulnerabilities. And we can't believe some Microsoft Surface devices still impacted, because usually this one is actually pretty much secure on many things. And we found 5 more bugs. So Dave, we will report them after the conference. And confidential computing is actually under the danger. Why? In many things, it's rely on our CPU's power and how it is executing and how the computation is happening. But also, like, we growing the number of cores, we growing the performance, but in many cases, to sacrifice for performance security, we're doing a lot of executions over the time simultaneously. We're increasing the cache, but we're not thinking how this cache used. It's been a great talk by Rodrigo Branco, who has actually been running a security team at Intel, which has been focusing also on microarchitectural attacks. It's been a keynote which has discovered a lot of political things going on behind all these disclosures happens with Spectre and Meltdown. I really recommend this video. And here's a timeline. So of the multiple vulnerabilities being discovered, and basically today I will be talk about the Spectre variant 1 and variant 2, which is still active on AMD-based silicon, on newer silicon, which has been released last year and year before. So complexity is actually not a friend of security, right? And our platforms, our hardware, is get more complex and complex over the time. This does not benefit us as a defenders, but in the same time, we continue to use the same practices. So we not get up with this complexity. And why Spectre strikes again? Exactly because of that. And we've been giving a talk at OffensiveCon, and of course enjoying an amazing keynote from the Dave Aitel. So Dave, we hear you. CPU is still a thing, and we should look deeper on the silicon stuff. And we started working on this research actually about like a 9 months ago, and we can't believe actually it is a real problem on the newer silicon. And we just take from the GitHub publicly available POC and test it. And then we realize actually it's working on ring 3. Then we move to ring 0, so we can actually break KSLR as well. And we've been experimenting with firmware. And firmware stuff is interesting. But before we get there, let's look on this mitigation testing tool. So basically, we run this tool on the most recent CPU from AMD, and it says the mitigation is actually in place, everything is secure, right? But we use exactly this platform for proving it's not that secure as we think. Our setup being with Ryzen Zen 2 and Zen 3, and we're pretty much sure it works on Zen 4, but platform didn't make at the time for this presentation. This is a GitHub link to the repository where POC, original POC we used for the modifications is stored. And actually, we just modify a bit, so you can see like this one is almost original, so basically we run it, so all the mitigations in place, and binarily is basically disclosed from another process. We leak these bytes, right? So on the left side, it's Zen 2. On the right side, it's Zen 3. So both are vulnerable for this one. And we prove ACLR, it's not a thing on the AMD silicon. What about ring 0 and KSLR? And for this one, we modify, of course, original POC to be suitable for executing on in the kernel mode on Linux. So let's guess. And as we can see, basically, it's still vulnerable. So basically, what I'm saying here, we need to trust mitigations, but we need definitely verify them. And some mitigations are more complex than others, and microarchitectural attacks is actually not very well understood by the industry. And basically, even make things worse, we not understand these attacks well, we not understand how to test them. And when we run the tool and it says the mitigations is active, we believe it is active. But as we can see, it can be different. On the firmware, we try to actually poke around how we can try to leak the secrets from the system management mode, and it's like a very privileged mode on x86 CPUs. In many cases, it's used like as a trust zone on ARM CPUs when it's basically isolated environment to execute some privileged stuff. And it happens for many years, and unfortunately not changing nowadays, but mitigations more and more increase it on the firmware, which is good. And basically what we did, we tried first ring-tree to SMM. Then we tried to understand why it's not working and tried to ring 0 to SMM. And of course, we tried also system management mode to system management mode because nowadays it's some of the mitigations like PPAM and some others try to isolate processes from each other. It will be interesting to see if it is broken. So what we did for system management instrumentation, because this is actually interesting. You can't just go and test your code into the firmware. So we implement the vulnerable driver. Come back to the platforms we pick for the testing. It's been kind of like probably not the best from the security perspective, but who cares, because it's same silicon on other CPUs, other platforms as well. And we basically develop our own driver. When we implement copy mem, it's basically a write primitive to the system management mode, where we can basically, from victim function, change easily the sampling, threshold, and many other functionality to experiment with the cache attacks. And after that, we actually also implement some sort of like a Python wrapper to make this instrumentation pretty quickly. Here is basically our implementation on ring-tree to SMM. And also, we need to shoot out to our active tool called Platbox. And Platbox is actually kind of like a very useful tool for research on AMD-based platforms. And we also send some modification and improvements for this platform as well, which we discover useful in our research. So it's already open sourced and upstream. Why we need a Platbox? We need to manipulate the physical memory from the operating system level. And basically, Platbox allow us to do this manipulation in a very handy way. So we did all these experiments, and we move from basically experimenting ring tree to SMM and ring 0 to SMM to actual SMM to SMM. And for making this function very handy, we implement all the primitives which we can actually change, shift some cache thresholds, and many other things. And this is a software semi-handler, which is basically being kind of like manipulating different timelines when the function called. As example, we can do random delay, which can also reflect on the results. So, and of course, we implement all the primitives you want to use. On the left side, on the screenshot, you can use like a different commands, secret we want to leak, different arrays, and debug buffer if we want some sort of like understanding what is going on. So it's complete instrumentation on the platform without having any debugging on it. So basically, it takes also a lot of time to actually implement all the setup to prove these bugs are legit. So basically, as we can see from that screenshot, different cache timelines and interactions are different, and it's not consistent and coherent. So another one, it's actually even show more data, but we not finish this research. So basically, we not prove we can leak a system management to a system management mode yet, but we're working on it. So, but why firmware? Speculative execution is still the thing, and it's a lot of problems in there. We also disclosed last year a vulnerability called firmware bleed, but it's fixed by Intel only this year. But unfortunately, at scale, it's also still unfixed. So what is firmware bleed is? It is some specific code which is implementing return stack buffer speculative barrier for actually not allow you to kind of disclose the buffer if speculative execution happens. So after the patch, you can see the routine for RSB is actually changed significantly, and it is increased like in performance for almost 5 times for this specific code pattern. And problem with this patch, of course, you don't want to, for every system management call, software SMI handler, to have such code be responsible for RSB. Because what will happen, it will cause significant delay, and this delay of performance delayed a lot of vendors to fix it. So our research shows, basically, we report in July 2022 to Intel PCERT. They not actually issued, and they said it's not an issue, but after that happens red bleed, when basically it's also related to return of stack buffer isolation. And basically it's the same thing, and it's been a problem. Then we communicate to Intel back and try to explain with more details and samples, even on the things they already knew about on red bleed and why they fix it. So then in May 2023, finally Intel fixed it, and it's been actually very great collaboration with them. And in May, and end of May, they also decided to even dedicate the entire web page for firmware bleed, because this is actually a big problem in the end. Of course, like it's not really dedicated for client computing, but when we're talking about the clouds, it actually breaks in many senses confidential computing. And as we can see, unfortunately, not all the vendors get fixed yet. And as you know, Supermicro, it's one of the vendors which is basically have one of the most common share of server market still unfixed. And performance issues, it's one of the things which is actually stop vendors to deliver these fixes. But of course, more mature on the product security vendors like Dell and HP, in some cases, they actually fix it. But as we can see, HP, Supermicro, it's not. And it will take time, but just to make things worse, some of the vendors even issued their own CVEs for firmware bleed, like IBM or Dell, and they increase the severity because, of course, original severity, it's kind of like a not very critical, but the severity comes from the industry, it's way more critical. And we have some bonus bugs. Today is a disclosure day for a few more reference code vulnerabilities. We've been thinking to disclose actually about 10 different vulnerabilities today, but they get extended, as I mentioned it on one of my first slides. And I will leave you with some information. We will go for our Black Hat Europe talk. And this one is very interesting because it's related to a lot of vendors and parsing routines for logo, which is turns when the system boots. And this one is very impactful because it's very easy to exploit when, of course, the primitives are in place. And also, in the same time, it can be already used in operations. We just don't know about it. So, unfortunately, the coverage of this issue is pretty significant. And basically, a lot of vendors are impacted, and even different independent BIOS developers like American Megatrends, Insight, and Phoenix. So this is our interim results for coverage of American Megatrends code. Why we did that? Because it also took some time for us to convince them about the problem. So thank you so much for your attention. But just as a closing remark, what I wanted to say, we focus a lot on operating system layer. We don't dive into the problems which go beyond and below the operating system. And this is a lot of things there, and it's already used by threat actors. We know about that. And it's things getting worse because we not pay much attention. We don't talk about it. We just basically don't see the problem because we don't look into the problem. But over the time, The code bases get more complex, hardware get even more complicated and complex as well, which is benefit attackers, not the defenders. So as an industry, we should keep up with such trends and work better on things below the operating system. Thank you so much.